most motions, like you can see, are pretty complex. And here's where center of mass steps in. It's gonna be the key with which we can unlock real life motions, where things are rotating and moving. Most of the bodies that we see are actually systems of infinitely many particles. So how exactly the center of mass gonna make our job of studying motion of these bodies easier? Let's pick one. Let's pick a box that's rotating as it's falling down, just like any normal box would do if you just rotate it and let it fall. If you pick a random point on this box, its motion is really complex, right? It looks like a spiraling motion that's going down as well. It's really hard to make sense of. But if you find what the center of mass of this box is, then going by what we just learned, it's only going to respond to the net external force on that box. Now, if you look at the box, the only net external force on it is gravity, the neglecting air resistance. Then, that center of mass is going to fall down in that straight line, even though the body of which it's a part is doing crazy things. So it's going to provide us with one single straight line path which we studied in 1D motion. Now, if that doesn't convince you about the center of mass simplifying things, let's pick something like a bowling pin, right? Ones that people used to juggle in a circus. If you throw one, it can go around like that and come down over here. But again, if you take a random point on that, its motion is going to be really complex. But if you do pick the center of mass of that bowling pin, the same rule is going to apply. The only external force on it is going to be gravity, which means the center of mass is going to traverse up. That's right, a parabola, as if nothing else is around it. Even though the body itself is taking a very, very complex path. If you look at the center of mass, it's moving in a beautiful parabola that you can study really easily. Now, these are examples that show you the center of mass symmetry. Now, if these aren't enough, let's pick something that you just learned in the previous chapter, collisions. Now, the main thing about collisions, why you can conserve momentum if you take two bodies colliding, is because the forces between them are internal, right? Now, that must also mean that if you take the whole of those two bodies as a system, then the net external force is zero, which means the center of mass must, that's right, before collision, during collision, after collision, doesn't make a difference as far as the center of mass is concerned, because none of the external forces are changing. Yeah. So if the external force is zero to begin with, it's going to remain zero throughout. So the beauty here is, if you now look at two bodies that are about to collide, yeah, and you can see the center of mass right now moving. Now they do collide and something else happens, and the bodies start moving in different directions with different speeds. But the center of mass continues on as if the collision didn't even happen. Because as far as the center of mass is concerned, that collision was something internal to the system. And like we understood, center of mass does not care about anything that happens internally. So in one sense of the word, the center of mass is truly the boss. There's a huge collision happening and it does not care about the collision at all. Acts as if the collision didn't even happen. It's like how an Indian movie is considered incomplete. And as an actor, you're considered a loser until you lost your bomb virginity. Now, what is this bomb virginity? You have to walk across the screen towards the camera with a scene of an explosion. You should walk with the smug satisfaction of an employee walking out of an office-sponsored buffet. And until you do this, and you turn back and look, and in that scene, until the audience claps and applauds crazily, you have not yet completed your role as an actor. And once you have, though, you become one of the privileged few who can fart out 100 crore movies every weekend. But the real boss is not really these guys, but the center of mass, because if a collision is internal, what really is an explosion? An explosion is just the second half of a collision, right? Coming together part and then getting out is a collision. You get out alone, that's an explosion. So the point is, even an explosion is just an internal force. And who doesn't care about anything internal? The center of mass, right? So if I do throw a bomb and somewhere in midair it explodes into multiple pieces, then all of those interactions were internal to the pieces of that bomb. Which means the only external force is still gravity, which is going to mean that the center of mass is going to continue on even after the explosion as if nothing happened. So the center of mass really qualifies to be a hero in our industry, because not only does it know how to walk out of an explosion as if nothing happened, it walks from right inside, not a single F given. So the next time it's Diwali and you've pestered your parents for this expensive fancy item which is like this big, and then you light it and it goes up and explodes beautifully and everybody's going, ooh. you're going to be going ooh as well, except that you're going to be doing it because you see an imaginary point that went up and came down unaffected by the explosion. And in this way, we've contaminated you for the rest of your life, because next time you see an explosion, you cannot not see the center of mass going up and coming down. Even if you see the angry bird, the blue one, exploding into three birds and then continuing, you will continue to notice that the center of mass is the three of them. If the laws of physics are obeyed in the game, which I think they are, will continue on unaffected. So now I want you to think by yourself about the apparent weightlessness of a ballerina. Now I want you to think about when the ballerina takes off, how does it look like? For a while she's floating, defying the laws of gravity. And I want you to think of what her center of mass could possibly be doing and how she can change the orientation of her body to make it seem like she is defying gravity for a while. And I want you to be assured it's only an illusion. Yeah? Now with these in place, we are ready to answer the question we began this with, which is, why is the Fosbury flop better than the other ways in which you can clear a high jump bar? And what makes it so revolutionarily beautiful? And also the question, why is this being asked in this chapter about center of mass? But if I were to ask the question, do you have to really get over the bar completely to clear the bar? You might ask, what does that question even mean? Let's find out what that means. So as you're thinking about what does it mean to say, do you have to completely get over the bar in order to clear it? Let's watch the scissor kick. And watch approximately what the center of mass of that high jumper is doing. Yeah, he's jumping over, and so is the center of mass at a height that's somewhat above the high jump bar. And if you look at the barrel roll, the center of mass is again clearing the high jump bar, but a little closer. So the amount of force required to do this will be lesser than for the scissor kick. But now, if you look in slow motion at the Fosbury flop, you notice that as the high jumper takes his jump, as he turns and takes his jump, and as he's going towards the high jump bar, the center of mass is consistently somewhere near the middle of his body. But as he begins to clear the bar and begins to start bending again, the center of mass is going closer and closer to that bar, but it has not yet crossed it. But just before it's going closer, his head is bent over and it's coming to the other side, keeping the center of mass still below. And then he brings his legs across, eventually falling and clearing the bar. So he has cleared the bar, but has the center of mass? It hasn't. It has actually passed below the bar. If that isn't a trick of physics, nothing else is. So what you have done is use the flexibility of your body. So Dick Fosbury traded his flexibility for an increase in strength, because now he knows the amount of force he must apply for to get the center of mass over is lesser, because he doesn't have to get the center of mass above. Right? Let's imagine he has a mass m. Then if you have to get the center of mass over the bar, you know the amount of force you must apply. Correct? Now in this case, what are you doing? For the same mass m, you're taking the center of mass below the bar itself. So the force you require is less. But what do you compensate that with? With your flexibility. By being able to take one part of your body over and make the fact that you're able to bend your body back again makes it so that your center of mass passes just below the high jump bar. Now the other questions that I asked you about how a tightrope walker is benefited by carrying a pole, or how do you decide when a chair must be balanced, the questions like these you will be able to answer after you learn about one more highly connected concept called center of gravity. You've learned about center of mass over here. Yeah, center of gravity is something that's very close but not the same. And once you learn about both of these, you can answer those questions really well. So you've come a long way. You began with the kinematics of a single point traveling along a straight line called 1D motion. From there you learned about 2D motion. Then we taught you Newton's laws, and then you learned about the ideas of energy, and then momentum, and then center of mass. Now with all this, you've unlocked one of the most beautiful parts of physics. So I invite you officially to rotational mechanics.